Hello, a very good morning, good afternoon, good evening to all the participants and the students. This is the course titled Multi-Criteria Decision Making and Application under the MOOC platform. As you know, this is a 12-week course, and each week we have 5 lectures, and each lecture is being from for half an hour. And this is the fourth lecture or slide, whatever you say, in the area as discussed about multi-criteria decision making, and my good name is Raghunandan Sengupta from the IME department at IIT Kanpur in India. So, if you remember, in the last lecture we were discussing about the optimization problem, and I said that considering the optimization problem, you have a set of constraints which are linear in nature, while the objective functions are in the initial stages they would be two separate objective functions, which are basically nonlinear in nature, which is basically a very simple quadratic equation based on the fact that you want to find out the optimum point for the finding of the maximum or the minimum for a circle, and there are two circles. And we will see that how we try to find out pictorially. Obviously, solution is given in the background. Pictorially, we try to find out how we can find out the optimum point both for the minimum, maximum for objective function 1, then for objective function 2, and then we try to find out the combined objective function, which will be f x 1, which is basically the first one, or f 1 as we say, and f 2, which is for the second objective function, and we try to find out the combined bi-objective function, which will be f 1 plus f 2. So, the coverage would be continuation of the example 6 which we are doing, and then as it proceeds we will try to basically start with the last example under the introduction, which is the 7th one. Now, considering the example which we were discussing, there were 4 constraints to find out that the overall area first will be a rectangle, and then we bring the last two constraint, which is the 5th and the 6th. It will result in an feasible area, which I had noted down in yellow color. I will again note it down in this lecture accordingly. So, the constraints are, I will mark and put a tick mark. The first constraint is x 1 is greater than 15, second one is x 1 is less than 90, the third one is x 2 is greater than 15, the fourth one is x 2 is less than 90. So, that forms the rectangle, and then we add the 5th and the 6th one, which is accordingly the 5th one is x 1 plus x 2 is greater than 60, x 1 plus x 2 is less than 90, and once you have that, the overall area I am just marking in yellow color, this is the feasible region. I am just marking the outline. So, if I colored the whole area, this is the overall space where you want to search for the optimal points. Now, considering the objective functions, if you remember, I did mention in the third lecture that there was a color combination for f 1, which is the objective function 1, and f 2, which is objective function 2, and that is why I marked those circles accordingly. So, if you concentrate on f 1, so this would basically have x 1 minus 15 whole square plus x 2 minus 30 whole square, and as I keep increasing the circle, at some point of time it touches, I am not considering f 2 only now. So, if I keep increasing f 1, at some point of time it touches the feasible region at some point, and then that would basically give me the minimum point, and then I keep increasing, that at some point of time it will leave, just touch the outermost boundary, which is x 1 plus x 2 is less than 90, and then keep increasing. So, we need to find out, number 1, the point at which the objective function f 1 will be minimum and also maximum inside inside at the boundaries of the feasible region or in certain internal points. And similarly, if I draw f 2, which is the second objective function, which is shown in blue color as I mentioned, similar analysis will be done, that it keeps increasing its concentric circles, it touches the feasible region space at some point. I am not going to derive it immediately, and then it goes inside the feasible region and then slowly touches the line x 1 plus x 2 less than 90, and then increases accordingly. In the process, do remember, at some point of time, depending on how the rate of increase of the radius of this f 1 objective function and f 2 objective function is, they will intersect, and that intersection point, some would be in the infeasible region, which is outside the yellow, and some would definitely be inside the feasible region, which is shown in yellow, and it will continue accordingly based on the fact we want to find out the minimum as well as the maximum. So, this is the idea, and obviously, if you can visualize, we will try to solve it accordingly. Now, first let us consider trying to minimize them separately. So, as it says, when they are separately, that is f 1 x and f 2 x are minimized, when you solve them, the solutions are accordingly. We will go into the details of trying to find out the optimum solution when it is a bi-objective or a multi-objective problem later on. But as I mentioned in the first lecture, solving this simple linear programming, single objective linear programming, single objective quadratic programming would be easy, and based on that fact we have that solution. That is what I am going to now highlight. So, if I separately minimize at the point x, which is 22.5, which is for x 1, and 37.5, which will be for x 2, it will interestingly satisfy the line x 1 plus x 2 is equal to 60, which was basically greater than 60. So, just as it touches that line, which is the corner line or corner point of that feasible region. So, that will be the point where f 1 will be minimized, and f 1, when I put the value coordinates, which I am now circling, the coordinates are, which have been found out, are 22.5 and 37.5. Putting that, we get the objective function f 1 is minimized and the value is 112.5. So, this is single. Similarly, when I concentrate on the objective function f 2, which is shown in the blue color, and with the different coordinates of the center with respect to f 1, the optimum point where it will give me the minimum solution would be 37.5 for x 1 and 22.5 for x 2. Based on that, when I solve, and also very interestingly I should mention, this is also a point which is on the boundary of the feasible region, and based on the fact that the line is x 1 plus x 2 is equal to 60, obviously greater than 60 are greater than equal to 60 are the set or the boundary conditions which were set. Based on that, when we find out the objective function f 2, the value also comes out to be very interestingly as 112.2. The objective functions for f 1 and f 2 separately are 112.5 for case 1, which is f 1, and for case 2, which is f 2, are same. But when we try to find out what is the coordinates based on which we get that objective function, they are different. For f 1, the optimum point, as I mentioned, again I am mentioning is 22.5 and 37.5, while for the case when I want to find out the optimum point for F2, it is 37.5 and 22.5. The corner points and the functional values as mentioned are illustrated in the diagram, and we will find out, and they highlight that the minimum values as well as the coordinates based on which we want to find out the optimum points for x1 and x2, such that we separately get the minimum point for f1 and the minimum point for f2. Now, let us consider some other sets of points also, and why I am going to say that. If you remember that, I will draw it here. If you remember the figure looked like this. So, this is the x2 x1 coordinate, so this I am trying to draw as the feasible region. There were two sets of points. So, this whole area is the feasible region. So, you have to find out the points accordingly. Now, for example, for the first objective function, I should use a different color as it was there, red. So, the concentric circles increases like this. And it goes on. So, the point which you see here where it touches is the case where we get the optimum point for f1 only. And if I concentrate on the second circle increases like this. I am trying to draw it as nicely as possible. Maybe the other diagram gives you that idea. So, for the case when I am trying to optimize only f2, the point which is given is here. So, this will denote by A2, A as the optimum point for the minimum case, and the suffix 2 is for the objective function 2. If I denote the first point, this is A1, again the optimum point is for the minimum case is denoted by A with the suffix 1 is for the objective function f1. Now, obviously, if you see, both of them start intersecting as they expand, and if I consider the corner points accordingly, and for our example, these corner points which you are going to consider are, I will highlight again, 1545 and 4515. If I do that, very interestingly, just for an example, that the objective function value only for f1 at 1545 comes out to be 225. So, 1545 would be some point as I keep x1 as 15 and x2 as 45. So, I go up. So, this circle center remains same, but it expands. So, it is 225, and if I put the same coordinates for f2, because f2 has is larger in the concentric radius, considering that point of 15 and 45, the corresponding value for f2 is 1125. So, I am doing it separately. So, if this is the case when we are considering the minimum point, just for example, if I go back to the earlier slide where it was mentioned that the values of f1 and f2 separately along with the coordinates, if you see, F1 was minimized and the minimum value was 112.2 at 22.5 and 37.5, while F2 was minimized, the minimum value was 112.2 again, and the coordinates were 37.5 and 22.5. So, if I want to compare, 112.5 is much less than these values of 225 and 1125. So, obviously, the points 1545 and 4515 would never be the minimum points based on the fact that we want to find out the minimum value for F1 separately and F2 separately. Now, if I consider the coordinates, just for example, 45 and 15, and I want to find out the values of F1 separately and F2 separately. Very interestingly, F1 value is equal to 1125, which you see as I draw is exactly equal to the value of F2, which was at the point 1545. So, obviously, a change in the coordinate and the corresponding change in the values of F1 and F2 are exactly the same. They are the same value. So, to further corroborate, check the value of F2 at 4515 and the value comes out to be 225. Now, for 4515, I am writing here, 4515 are the coordinates for x1, x2, and if I find out the corresponding value of F1. So, this would be F1 is also 225, but very interestingly the coordinates are just switched. So, if you concentrate and try to visualize, the values of 1125 or 225, the values are definitely not minimum based on the fact what you have found out, but the rate of increase of these two concentric circles, if they are at the same rate increase, then the loci of the minimum points would slowly be a straight line moving along this direction. This is not really needed for this course, but I thought if you can visualize, it will give you an idea that how both the objective function separately and collectively can be optimized. I am not gone into the maximization yet. If we now consider the minimization of the both the objective function together simultaneously. So, this is what is important for us to understand. Under the same set of constraints as you remember was 6 in number, then the common point which satisfies, considering the fact we want to minimize, would be very interestingly a different point, which is now x 1 is 30, x 2 is 30, and it will satisfy the line x 1 plus x 2 is just equal to 60, because the one of the boundaries of the feasible region was x 1 plus x 2 is greater than equal to 60. So, if I draw it for point 1, so this is x 2, this is x 1, so at a point which is 30 30, I will try to draw so the point will be 30 30 inside, such that is on the point the surface where they are satisfied. So, some point here which will be satisfied by both of them, and the optimum value which I will denote by A, sorry the color should be red, again A is for the minimum, and I denote it as A 1 comma 2 corresponding to the fact that I am trying to optimize both 1 and 2 combined. And when I put the values of the coordinates x 1 x 2 30 30 and I try to find out the overall combined objective function, which is f 1 plus f 2, very interestingly it comes out to be 225. Now, what remember the values, 112.5 was the single objective function minimum value for f 1, then again 112.5 was the single objective function for f 2 with coordinates which were different. But interestingly, when I combine them, the combined f 1 plus f 2 coordinate system is just the sum which is you see, which is 225 as shown in the second bullet point, and the coordinates are also different. So, for minimum for f 1, f 1 minimum, which were denoted by a 1, was some x 1 star, the values I have repeated many times. So, I am going to repeat it again. For when I am trying to separately minimize f 2, which was a 2, you will have another x 1 double star, say for example, which was already given x 2 double star, and very interestingly, which you know, these two values were equal and these two values were equal separately, but combined, very interesting, again the sum is basically for the sum is basically f 1 minimum plus f 2 minimum, which is 225, and the coordinate system is no longer x 1 star, x 2 star or x 1 double star, x 2 double star. The point comes out to be 30 comma 30. This is intuitive based on the fact that the common coordinate in x, which is 30 30, is minimize both the functions simultaneously. So, one thing should be remembered, leave aside the minimum point for x 1 or x 2, f 1 or f 2 or combined, they are different, obviously they would be, and the coordinate system based on which we are trying to find out the minimum point of f 1 or the minimum for f 2 or the combined would also be different. So, this is the last part which we will be concentrate for throughout the course, is basically to find out the point which we found out as 30 30, which will give the best solution for the combined objective function of f 1 and f 2, and that common point which is 30 30 here need not give us the optimum point for f 1 separately or f 2 separately, and this would basically be the main idea of the study throughout the course in different examples. For illustration, just to extend that example, one can check, and I am stating few values here for the coordinate system and the coordinates and the corresponding values of f 1 and f 2 also. So, on there are 5 bullet points starred given in the star mark, and the values of the coordinate system x 1 x 2 I am repeating. The first one is 22.5, 37.5, and the values when you put it in the equation, the combined objective function comes out to be 675. Similarly, when the values are 37.5 and 22.5, the combined objective function value also again comes out to be 675, and this is a very interesting fact. If you see repeatedly as I go, the combined objective function value remains same, which is 675. For a third case, if it is the coordinates at 45 15, the value which I found out for the combined objective function f 1 f 1 plus f 2 now comes out to be 1350, again by interchanging the coordinates of just 1 minute. Interchanging the coordinates of x1, x2 as they become 1545, very interesting, the objective function remains the same. And for the case when they are 3030, the combined objective function, remember the combined objective function is 450. Very interestingly, at 3030 they give us the minimum point which was 225, minimum point for that point 3030, not the global minimum which is the best solution for F1, which was 112.5 for F1, separately 112.5 for F2 also. So, combined if I find it out and then solve the problem based on the fact that the solutions have to be found, then the combination comes out to be 450 accordingly. Now, if I plot the coordinates in a two dimensional diagram, and what are the coordinate system? On the x axis I have x1, and on the y axis I have the combined objective function. It is no longer a single objective f1 plus f2, and if I draw the graph, so it becomes a very nice quadratic function. Obviously, this is a quadratic equation. If you remember, f1 was a quadratic equation, f2 was a quadratic equation, combining them would definitely give me a quadratic equation. What is interesting is, when I find out the values for f1 plus f2 for different coordinate system of x1. So, obviously, x1 it can be done for x2 also, but I am just highlighting for the case when it is x1. So, similarly, you can have a diagram for x2 also. So, the minimum point where the objective function would be, if you remember, the values were given as 3030 coordinate system, and the objective function comes out to be 450. So, as I keep increasing x1, obviously, x2 will also change, or I keep decreasing x1, x2 will also change. The minimum point is always found out to be an optimum point, which is now 3030. It is not the best point if I consider separately for x1, separately for x2. So, based on that, you will understand that trying to find out the best optimum solution for a combined objective function or a bi-objective or a multi-objective would not give you the same result based on the decision variables, which is x1, x2 here, as well as the objective function accordingly. So, this was the discussion for us, the example 6, based on the fact that we are trying to consider the minimization. Later on in the next class, which will be the 5th lecture, we will consider the ideas of trying to find out the maximization for the same problem. And once you understand that, considering that the objective function, as I mentioned, is nonlinear, which is quadratic, and the constraints are linear, then slowly we will try to expand that example for other cases and then discuss other topics under the ideas of MCDM. Thank you very much. Have a nice day.